Most of the stars you see in the sky are not alone. Around them circle mysterious worlds, planets covered in diamond, horizons with two suns, rains of molten iron. But what secrets are they still hiding from us? Picture ancient Babylonian astronomers on rooftop terraces, tracking a peculiar wandering star that raced across dawn skies faster than any other. They called it Nabu, messenger of the gods. Night after night, scribes etched cuneiform tablets by flickering oil lamps, recording Mercury's swift 88-day orbit. Yet this tiny world, closest to our sun, remained stubbornly mysterious. Early telescopes revealed nothing but a shimmering dot. For centuries, astronomers wondered if Mercury was tidally locked, showing only one face to the sun, the Mariner. 10 mission in 1974 finally unveiled a cratered, airless world of extreme temperatures, shattering romantic notions of a perpetually twilight hemisphere where life might hide. What other cosmic neighbors have we completely misjudged from our distant earthly perspective? Ancient Greeks thought they saw two separate stars, calling the morning apparition Phosphoros and the evening one Hesperos. For millennia, Venus symbolized beauty and love, its dazzling brightness inspiring poets and lovers. Early 20th century astronomers imagined steamy tropical jungles beneath those mysterious clouds, a world where dinosaurs might still roam. Science fiction writers dreamed of Venusian civilizations thriving in perpetual mist. But when Soviet Venera probes finally pierced the veil in the 1970s, they revealed hell itself. Surface temperatures hot enough to melt lead, crushing atmospheric pressure, and clouds of sulfuric acid. The romantic Venus died in those moments, replaced by a cautionary tale of runaway greenhouse effects. Our beautiful morning star became a warning about what Earth might become. How many of our cosmic dreams dissolve when we finally reach out to touch them? Giovanni Schiaparelli peered through his telescope in 1877, sketching what he called canali, channels on Mars. When translated to English as canals, the word sparked decades of fevered speculation. Percival Lowell spent fortunes building observatories, mapping intricate waterway networks he believed proved intelligent Martian engineering. Books, movies, and radio broadcasts brought Martian civilizations into popular culture. H.G. Wells's War of the Worlds terrified audiences who half believed such neighbors existed. Astronomers spent cold nights sketching seasonal changes they interpreted as vegetation cycles. The Viking missions of 1976 shattered these dreams, revealing a barren, frozen desert. No canals, no cities, no little green beings, just rust-colored rocks and empty plains. Mars became a ghost story of what we desperately wanted to find but never did. Why do we project our deepest hopes onto distant worlds that can never fulfill them? On January 7, 1610, Galileo Galilei pointed his handmade telescope at Jupiter and saw what no human had ever witnessed: 4 tiny stars arranged near the giant planet. Night after night, he sketched their positions, watching them dance around Jupiter in perfect mathematical harmony. These weren't stars at all, but moons, worlds orbiting another world. The discovery shattered the ancient belief that everything revolved around Earth. Church authorities condemned Galileo's findings as dangerous heresy, yet Io, Europa, Ganymede, and Callisto continued their eternal waltz, indifferent to human politics. By candlelight, Galileo calculated their orbital periods, unknowingly documenting some of the most fascinating worlds in our solar system. Europa's hidden ocean, Io's volcanic fury, and Ganymede's magnetic field would remain secrets for centuries more. His simple observations planted seeds of cosmic revolution. What other revolutionary truths are hiding in plain sight, waiting for someone brave enough to look? In 1610, Galileo's primitive telescope revealed something impossible. Saturn seemed to have handles, or ears, protruding from its sides. Frustrated astronomers spent decades trying to understand this cosmic riddle. Some drew Saturn as a triple planet, others as a world with two large moons touching its surface. The mystery deepened when Saturn's appendages periodically vanished completely, leaving observers baffled. Christian Huygens finally solved the puzzle in 1659, realizing Saturn was surrounded by a thin, flat ring. But this answer birthed new questions. What were these rings made of? How did they form? Centuries passed before scientists understood they were countless ice and rock fragments, shepherded by hidden moons. The Cassini mission revealed rings of incredible complexity, braided strands, radial spokes, and gravitational sculptures carved by tiny moonlets. Saturn transformed from a simple wandering star into a masterpiece of celestial mechanics. How many everyday mysteries surround us, waiting patiently for the right moment of understanding to arrive? William Herschel wasn't looking for new worlds on March 13, 1781. The amateur astronomer and professional musician was simply cataloging stars from his backyard in Bath, England. Through his handmade telescope, he noticed a peculiar disc-shaped object that seemed different from the pinpoint stars surrounding it. Initially, Herschel thought he'd discovered a comet. For months, astronomers across Europe tracked the mysterious object, calculating its orbit. Slowly, the stunning truth emerged. This was no comet, but an entirely new planet, twice as far from the Sun as Saturn. Suddenly, the solar system doubled in size. Herschel became famous overnight, earning a pension from King George III. He named his discovery Georgium Sidus, George's star, in the king's honor. Later, astronomers settled on Uranus, after the Greek god of the sky. This frozen world of methane clouds and sideways rotation expanded humanity's cosmic address beyond all previous imagination. What other universes of possibility await just beyond the edge of our current vision? By the 1840s, Uranus was misbehaving. Its orbit wandered from predicted paths, suggesting an invisible gravitational influence tugging at the distant world. Young mathematician Urbain Le Verrier spent months hunched over calculations by gaslight, using Newton's laws to predict where an unknown planet must be hiding. Meanwhile, English mathematician John Couch Adams worked on identical calculations in Cambridge. Le Verrier sent his coordinates to Berlin Observatory, where Johann Galle found Neptune within 1 degree of the predicted position on September 23, 1846. The discovery sparked international controversy over credit, but Neptune itself remained serenely indifferent to human disputes. This ice giant, with winds reaching 1/200 mph, became the first planet discovered by mathematical theory rather than accidental observation. Dark, distant, and impossibly far from the sun's warmth, Neptune proved that human minds could reach into the cosmic darkness and find truth through pure reasoning. What other invisible realities surround us, waiting to be discovered by the power of human thought? Clyde Tombaugh spent cold Kansas nights in 1930, methodically photographing the same star fields with Lowell Observatory's 13-inch telescope. Day after day, he compared photographic plates through a blink comparator, searching for objects that moved against the stellar background. On February 18, 1930, a tiny shifting dot caught his attention. Pluto had been found, the 9th planet, completing our solar system's family. For 76 years, Pluto reigned as the smallest, most distant planet, inspiring children's mnemonics and textbook diagrams. But improved telescopes revealed uncomfortable truths. Pluto was smaller than Earth's moon, accompanied by a relatively large companion called Charon. The Kuiper Belt held thousands of similar objects. In 2006, astronomers reclassified Pluto as a dwarf planet, breaking the hearts of a generation who'd grown up with 9 planets. Yet New Horizons' 2015 flyby revealed Pluto's surprising beauty. Heart-shaped plains, nitrogen glaciers, and complex weather patterns proving that size doesn't determine wonder. How do we balance scientific accuracy with the emotional connections we form to cosmic discoveries? In 1992, radio astronomers Alexander Wolszczan and Dale Frail made an announcement that changed everything. They'd found planets orbiting a pulsar, a spinning neutron star 1,000 light-years away. But these weren't the Earth-like worlds of science fiction dreams. These planets orbited a stellar corpse, bathed in deadly radiation, formed from the debris of their star's violent death. The discovery seemed almost cruel. The first confirmed exoplanets were utterly hostile to life. Astronomers spent sleepless nights analyzing radio pulses, measuring tiny timing variations that revealed these distant worlds. The planets, designated PSR B257 plus 12b, C, and D, became cosmic orphans, forever circling their dead parent star. Yet their discovery opened floodgates of possibility. If planets existed in such extreme environments, they must be everywhere. The cosmos suddenly seemed less lonely, even if these first worlds offered no hope of companionship. Humanity had taken its first steps toward understanding that planetary systems fill the universe. What does it mean to discover we're not unique, even in the most hostile places imaginable? In 2015, NASA's Kepler Space Telescope identified something extraordinary. A planet orbiting within the habitable zone of a sun-like star 1,400 light-years away. Kepler 452b became known as Earth's cousin, 60% larger than Earth, receiving similar amounts of stellar energy, potentially harboring liquid water on its surface. Scientists spent months analyzing tiny light dips as the planet transited its star, measuring its size, orbit, and possibilities. The discovery ignited imaginations worldwide. Could this world have oceans, continents, perhaps even life? Yet Kepler 452b remains tantalizingly beyond reach. Even traveling at light speed, the journey would take 1,400 years. We can only wonder about its skies, seasons, and secrets from afar. The planet exists in a realm of pure possibility, close enough to detect, far enough to remain forever mysterious. It represents both humanity's greatest discovery and deepest longing, proof that Earth-like worlds exist, coupled with the sobering reality that they're impossibly distant. How do we cope with discovering paradise worlds we can never hope to visit? You're floating in the gentle darkness now, where a forgotten world once held planetary status before vanishing into obscurity for 2 centuries. Giuseppe Piazzi discovered Ceres on New Year's Day 1801, tracking what he thought was a comet from his observatory in Palermo. Night after night, the Sicilian monk recorded positions of this mysterious object between Mars and Jupiter. As months passed, astronomers realized Ceres followed a planetary orbit, making it the 8th planet of our solar system. For decades, textbooks listed Ceres alongside Mercury and Venus. But then came troubling discoveries. Pallas, Juno, Vesta, similar objects in the same region. Suddenly, Ceres seemed less unique, relegated to asteroid status as the belt between Mars and Jupiter filled with rocky debris. The Dawn spacecraft's 2015 arrival revealed Ceres' secrets: a dwarf planet with possible subsurface oceans, bright salt deposits, and organic molecules. This humble world, demoted and forgotten, quietly harbors more ingredients for life than many larger planets. Why do we consistently underestimate the small worlds that might hold the greatest surprises? You're settled into perfect stillness now, contemplating a distant planet literally dissolving into space like morning mist touched by sunlight. In 1999, astronomers detected something unprecedented: a planet transiting its star, temporarily dimming the light as it passed between us and its parent sun. HD 209458b, nicknamed Osiris, became the first exoplanet observed crossing a stellar disk. But this gas giant harbored dark secrets. Orbiting just 4 million miles from its host star, 8 times closer than Mercury to our Sun, the planet endures temperatures exceeding 1,800 degrees Fahrenheit. Hubble Space Telescope observations revealed the impossible. This world is literally evaporating, streaming hydrogen, carbon, and oxygen into space like a cosmic comet tail. Scientists calculated that Osiris loses about 10,000 tons of material every second, slowly dissolving under its star's relentless radiation. The discovery shattered assumptions about planetary survival. Here was a world caught in its death throes, teaching us that planets aren't permanent fixtures, but temporary arrangements of matter, sometimes lasting billions of years, sometimes not. What does it mean to witness a world's slow suicide from across the galaxy? You're wrapped in cosmic contemplation now, pondering the closest possible destination for humanity's first steps beyond our solar system. In 2016, astronomers announced the discovery that changed everything: a potentially habitable planet orbiting Proxima Centauri, our nearest stellar neighbor just 4.24 light-years away. Proxima b represents the closest we might ever come to finding a second Earth within reach of human exploration. The planet orbits within its red dwarf star's habitable zone, where liquid water could exist on its surface. But this nearby paradise comes with harsh realities. Proxima Centauri unleashes deadly stellar flares that could strip away any atmosphere. The planet likely shows one face perpetually to its star, creating a world of eternal day and eternal night. Scientists spend sleepless nights analyzing radial velocity data, measuring the tiny wobble Proxima b creates in its parent star. Even at light speed, reaching this world would take over 4 years. Yet it remains our most realistic target for interstellar exploration, a tantalizing glimpse of possibility hanging just beyond our grasp. Is being so close to another potentially habitable world a gift or a cruel cosmic joke? You're drifting deeper into wonder now, imagining storms of molten titanium falling like silver rain on a world where the very air burns. WASP 12b challenges every assumption about planetary weather. This gas giant, discovered in 2008, orbits so close to its star that dayside temperatures reach 4,600 degrees Fahrenheit, hot enough to vaporize iron. The Super-WASP survey spent years monitoring stellar brightness, detecting the tiny dips that revealed this hellish world. But WASP 12b's most extraordinary feature emerged from spectroscopic analysis. Its atmosphere contains vaporized metals that condense into liquid droplets on the cooler night side. Imagine storms where titanium, vanadium, and chromium fall as metallic rain, pooling in molten lakes under alien skies. The planet's extreme heat creates winds exceeding 3,000 mph, carrying these metal vapors around the globe in perpetual circulation. Tidal forces from its nearby star stretch WASP 12b into an egg shape, while stellar radiation slowly boils away its atmosphere. This world exists at the absolute edge of planetary survival, a laboratory of impossible chemistry. What other impossible worlds await discovery in the space between science and imagination? You're nestled in perfect comfort now, contemplating a world where Luke Skywalker's binary sunset isn't science fiction, but everyday reality. In 2011, NASA's Kepler mission discovered something straight from Star Wars: a planet orbiting 2 stars simultaneously. Kepler 16b became the first confirmed circumbinary planet, forever linked to the iconic twin sunset scene from Tatooine. The discovery required years of patient observation, as astronomers detected complex light variations created by eclipsing binary stars and their orbiting planet. Every 229 days, this Saturn-sized world completes one orbit around both stars, experiencing double sunrises and sunsets. But unlike the warm desert world of science fiction, Kepler-16b remains a cold gas giant, too distant from its stellar parents to support liquid water. The gravitational dance between three celestial bodies creates orbital chaos that makes the planet's path wobble unpredictably. Scientists had to develop entirely new computational methods to model such complex dynamics. This world proved that nature surpasses fiction, creating planetary systems more exotic than any movie could imagine. Why does reality consistently exceed the boundaries of our wildest fictional dreams? You're breathing in the gentle night now, contemplating a world that might be watching us back from its perfect position in space. 22 light-years away, in the constellation Scorpius, lies a planet that captured imaginations worldwide. Gliese 667cc, discovered in 2011, orbits within the habitable zone of a red dwarf star, receiving just enough energy to potentially harbor liquid water oceans. This super-Earth contains at least 4 times our planet's mass, creating surface gravity that would make humans feel twice their normal weight. The discovery emerged from years of radial velocity measurements, detecting the gravitational tug this world creates on its parent star. Gliese 667cc became a media sensation, frequently cited as humanity's best prospect for finding life beyond our solar system. But its red dwarf host star creates challenges. Tidally locked rotation means one hemisphere faces permanent day while the other endures eternal night. Stellar flares could strip away protective atmospheres. Yet between the scorching day side and frozen night side might exist a twilight zone of perfect temperatures, where alien life could thrive. What civilizations might be gazing back at us from that eternal twilight border? You're settling into that perfect state of tranquil curiosity now, pondering a distant rocky world that mirrors our own in almost every meaningful way. In 2015, scientists announced the discovery of Kepler-442b, a planet so Earth-like it topped every habitability index. Located 1,200 light-years away, this rocky world orbits within its star's habitable zone, receiving 70% of the energy Earth gets from our Sun. The planet's size suggests solid ground rather than gas, with gravity similar enough to Earth that humans could potentially walk on its surface. Kepler's patient observations revealed a 112-day orbital period, placing Kepler-442b at the perfect distance for liquid water to exist. Computer models suggest this world could maintain stable temperatures for billions of years, long enough for complex life to evolve. The discovery process required analyzing thousands of brightness measurements, searching for the subtle dimming that occurs when planets transit their stars. Yet despite its promise, Kepler-442b remains completely theoretical. We can only imagine its seasons, weather patterns, and whether blue skies arch over continents we'll never see. How do we find meaning in discovering paradise worlds we can never hope to reach? You're wrapped in cosmic wonder now, as we explore one of the newest additions to humanity's catalog of potentially habitable worlds. In 2024, NASA's TESS mission identified TOI 715b, a super-Earth orbiting within the conservative habitable zone of a nearby red dwarf star. Just 137 light-years from Earth, this world represents our closest opportunity to study a potentially habitable planet with current technology. The discovery required months of precise photometry, measuring minute changes in stellar brightness as the planet completed its 19-day orbit. TOI 715b receives stellar energy comparable to Venus, placing it at the inner edge of habitability where greenhouse effects could create temperate surface conditions. Scientists immediately began planning follow-up observations with the James Webb Space Telescope, hoping to analyze the planet's atmosphere for signs of water vapor, oxygen, or other biosignatures. The world's proximity makes it an ideal target for atmospheric characterization, potentially becoming the first exoplanet where we definitively detect signs of habitability. Each new data point brings us closer to answering humanity's most profound question about cosmic loneliness. What will it mean for our species when we finally prove we're not alone? You're drifting into peaceful contemplation now, pondering a distant world where water vapor dances through alien skies beneath clouds we can barely comprehend. K2-18b made headlines in 2019 when Hubble Space Telescope observations revealed water vapor in its atmosphere, the first detection of water on a potentially habitable exoplanet. Located 124 light-years away, this sub-Neptune orbits within its red dwarf star's habitable zone, receiving similar amounts of stellar energy as Earth. The discovery required years of spectroscopic analysis, carefully separating the planet's atmospheric signature from its host star's overwhelming light. Scientists detected not just water vapor, but also hydrogen and helium, suggesting a thick atmosphere that could maintain liquid water on the surface. But K2-18b remains enigmatic. Is it a rocky world with a thick atmosphere, or a mini Neptune with no solid surface at all? Recent James Webb observations hint at clouds containing methane and carbon dioxide, painting a picture of complex atmospheric chemistry. This world exists at the boundary between terrestrial planets and gas giants, challenging our understanding of planetary classification. Why do the most promising worlds always seem to hover just beyond our ability to fully understand them? You're settling into complete serenity now, contemplating a cosmic symphony where 7 Earth-sized worlds dance in gravitational resonance around a distant star. In 2017, astronomers announced the most extraordinary planetary system ever discovered. 7 Earth-sized planets orbiting the ultra-cool dwarf star TRAPPIST-1. Just 40 light-years away, these worlds exist in a chain of gravitational resonances, their orbits locked in mathematical harmony like celestial music. The discovery emerged from years of patient observation, first with ground-based telescopes, then confirmed by NASA's Spitzer Space Telescope. 3 of the 7 planets orbit within the habitable zone where liquid water could exist. Scientists spent countless nights analyzing transit data, measuring each world's size, mass, and orbital characteristics. The system's compact nature means all 7 planets would fit within Mercury's orbit around our Sun, creating a pocket solar system of unprecedented complexity. Computer simulations suggest these worlds likely show tidally locked faces to their star, with permanent day and night sides. Yet between scorching day and frozen night, each planet might harbor temperate twilight zones where life could flourish. What does it mean to discover an entire family of worlds that could potentially harbor life? You're wrapped in gentle wonder now, imagining crystalline storms falling like precious jewels across an alien world where treasure literally drops from burning skies. HATP-7b orbits so close to its host star that atmospheric temperatures reach 4,800 degrees Fahrenheit. The Hungarian Automated Telescope Network discovered this gas giant in 2008, revealing a world where extreme heat creates impossible weather. Scientists analyzing Kepler data found that HATP-7b's atmosphere contains vaporized corundum, the mineral that forms sapphires and rubies on Earth. On the scorching day side, these gemstones exist as gas, but powerful winds carry the vapor to the cooler night side, where it condenses into tiny crystalline droplets. Imagine storms where sapphires and rubies fall like glittering rain, accumulating in drifts of precious gems across a landscape no human will ever see. The planet's extreme day-night temperature difference drives winds exceeding 3,000 mph, creating perpetual gemstone hurricanes. This world transforms our most valued treasures into mere weather phenomena, reminding us that rarity depends entirely on perspective. What other treasures become commonplace when viewed through the lens of cosmic abundance? You're settling into peaceful contemplation now, pondering a world that perfectly mimics Earth's size and temperature while harboring deadly secrets beneath its familiar facade. In 2015, Kepler 438b topped every habitability index, earning recognition as the most Earth-like exoplanet ever discovered. Located 470 light-years away, this rocky world receives 40% more energy from its red dwarf star than Earth gets from our Sun, placing it squarely within the habitable zone. The planet's radius measures just 12% larger than Earth's, suggesting similar gravity and possibly familiar landscapes of continents and oceans. For months, scientists celebrated finding our planet's closest twin, but follow-up studies revealed a sinister truth. Kepler 438b's host star unleashes catastrophic superflares every few hundred days, each one 10 times more powerful than anything our Sun produces. These stellar outbursts strip away atmospheric layers, bombarding the surface with deadly radiation. Any life on this seemingly perfect world faces regular extinction events that make Earth's worst disasters seem gentle. The discovery taught us that habitable zones mean nothing if stellar violence makes survival impossible. Why do the most promising worlds consistently hide the most devastating secrets? You're drifting into tranquil curiosity now, contemplating a world entirely covered by oceans so deep that strange forms of ice exist at crushing depths. GJ 1214b, discovered in 2009, represents something unprecedented in our solar system, a true water world. This super-Earth, located 48 light-years away, appears to be covered entirely by a global ocean hundreds of miles deep. The MERTH project detected this world through careful monitoring of stellar brightness variations, revealing a planet 2.7 times Earth's diameter with a density suggesting substantial water content. But GJ 1214b's oceans exist under conditions impossible on Earth. Surface temperatures reach 450 degrees Fahrenheit, creating a perpetual steam bath where the boundary between liquid and gas becomes meaningless. At greater depths, immense pressure compresses water into exotic forms of ice that remain solid despite scorching temperatures. Scientists spent years analyzing transmission spectra, trying to peer through the planet's thick, steamy atmosphere. This world challenges every assumption about planetary habitability, existing as a hot, humid greenhouse where traditional concepts of climate and weather break down completely. What forms of life might thrive in oceans that exist beyond our earthly understanding of water? You're nestled in cosmic wonder now, imagining a world where continents of liquid rock flow like slow rivers beneath skies raining pebbles of stone. CoRoT 7b, discovered by the French space telescope CoRoT in 2009, became the first confirmed rocky exoplanet smaller than Neptune. But this Earth-sized world exists in conditions that redefine the meaning of hellish. Orbiting just 1.6 million miles from its host star, CoRoT 7b completes one orbit every 20 hours, while showing the same face perpetually to its sun. The day side reaches temperatures exceeding 4,000 degrees Fahrenheit, hot enough to vaporize rock. Scientists believe this world once possessed a substantial atmosphere, possibly even oceans, before stellar radiation stripped everything away, leaving only a molten core. The planet's surface likely consists of lava oceans with weather systems made of vaporized rock. On the cooler night side, silicate vapor condenses and falls as tiny pebbles of stone. Imagine rain made of quartz and feldspar, storms of liquid granite, and aurora displays created by glowing metal vapor. This world represents Earth's distant future when our sun expands and boils away everything we know. How do we comprehend worlds that exist in states of matter our planet has never experienced? You're breathing in the gentle night now, contemplating humanity's first confirmed rocky world beyond our solar system, a discovery that opened floodgates of planetary possibility. Kepler 10b earned a place in history as the first definitively rocky exoplanet confirmed by NASA's Kepler mission in 2011. This world, 1.4 times Earth's size, orbits so close to its sun-like star that it completes one revolution every 20 hours. The discovery required years of careful analysis, combining Kepler's transit observations with ground-based radial velocity measurements to confirm the planet's rocky composition. Surface temperatures on Kepler 10b reach 2,500 degrees Fahrenheit, hot enough to melt copper. The day side likely consists of molten rock oceans under an atmosphere of vaporized stone, while the night side might harbor lakes of liquid lava cooling under alien stars. This world shattered the notion that rocky planets must be temperate. Scientists realized that terrestrial worlds could exist in forms completely unlike Earth, expanding our definition of what constitutes a planet. Kepler 10b became the prototype for an entire class of superheated rocky worlds that dominate exoplanet catalogs. Why did discovering our first rocky exoplanet force us to completely reimagine what Earth-like truly means? You're settling into perfect stillness now, contemplating a world that spins in the opposite direction of its orbit, defying every rule we thought governed planetary formation. WASP 17b challenged fundamental assumptions about how planets should behave. Discovered in 2009, this gas giant orbits its star in the opposite direction to the star's rotation, a phenomenon called retrograde motion that shouldn't exist according to standard planetary formation theories. The wide-angle search for Planet Survey detected this anomaly through careful analysis of transit timing and stellar wobble measurements. Scientists spent months verifying the impossible data, confirming that WASP 17b somehow acquired a backwards orbit during its formation. The planet also holds records for extreme bloating, with a radius twice that of Jupiter, despite containing only half Jupiter's mass. Its atmosphere has been puffed up by intense stellar heating, creating a world with density similar to styrofoam. The discovery forced astronomers to reconsider planetary migration theories, suggesting that gravitational interactions can flip entire worlds backwards during their youth. WASP 17b orbits in cosmic rebellion, a reminder that the universe consistently surprises us. What other fundamental assumptions about cosmic order are waiting to be overturned by rebellious worlds? You're wrapped in tranquil wonder now, imagining a world colored the perfect shade of ocean blue while enduring storms of razor-sharp glass shards. HD 1189733b appears deceptively beautiful in Hubble Space Telescope images, a brilliant blue dot reminiscent of Earth from space. But this gas giant's azure hue comes from something far more sinister than oceans. The planet's atmosphere contains silicate particles that scatter blue light, creating its striking color. Discovered in 2005, HD 1189733b orbits just 2.9 million miles from its host star, completing one orbit every 2.2 days. The close proximity creates extreme weather. Winds reaching 5,400 mph carry clouds of tiny glass particles around the globe. On this world, it literally rains glass sideways, driven by hurricane-force winds that never cease. Temperatures reach 1,700 degrees Fahrenheit, hot enough to vaporize metals. The day-night temperature difference drives perpetual glass storms that would shred anything in their path. Spectroscopic analysis revealed water vapor, carbon monoxide, and methane in the atmosphere. But these familiar molecules exist in an alien environment of flying glass and endless wind. Beauty and terror coexist on this blue marble of destruction. Why do the most visually stunning worlds often harbor the most hostile environments? You're drifting into cosmic contemplation now, pondering a planet that shouldn't exist according to every theory of planetary formation, yet orbits its star in defiant reality. Kepler 78b broke the rules of physics when astronomers discovered it in 2013. This Earth-sized rocky planet orbits so close to its host star that it completes one revolution in just 8.5 hours, faster than any known planet. At this distance, the world receives 3,000 times more stellar energy than Earth, creating surface temperatures exceeding 3,600 degrees Fahrenheit. The planet's existence poses fundamental questions. How did it form so close to its star without being destroyed? Current theories suggest rocky planets can't survive at such extreme distances, where stellar winds and radiation should have vaporized any solid material during formation. Yet Kepler 78b persists, its molten surface glowing red-hot as it races around its star. Scientists believe this world represents a planetary death spiral, slowly spiraling inward due to tidal forces until stellar gravity finally tears it apart. The planet challenges our understanding of where rocky worlds can exist, forcing us to expand the boundaries of the possible. Kepler 78b serves as a cosmic laboratory for extreme planetary physics. What other impossible worlds are orbiting distant stars, waiting to shatter our scientific assumptions? You're nestled in gentle curiosity now, contemplating a world so bloated by stellar heat that it defies our understanding of planetary density and structure. Qatar 1b, discovered in 2010, represents an extreme example of atmospheric inflation caused by proximity to its host star. This gas giant, located 550 light-years away, orbits so close to its sun that it completes one revolution in just 1.4 days. The Qatar Exoplanet Survey detected this world through precise photometry, measuring the minute dimming that occurs when the planet transits its star. But Qatar 1b's most striking feature is its inflated size. Despite containing 20% more mass than Jupiter, it measures 16% larger in radius. The close stellar proximity heats the planet's atmosphere to over 2,000 degrees Fahrenheit, causing the gas to expand like a cosmic balloon. Scientists studying this world discovered that intense stellar radiation can puff up planetary atmospheres far beyond normal limits. The planet exists in a delicate balance between gravitational compression and thermal expansion, creating a world with density similar to cork. Qatar 1b teaches us that planets are dynamic entities, constantly responding to their stellar environments. How many other worlds are being slowly transformed by the very stars that gave them birth? You're breathing in perfect tranquility now, contemplating a world that might harbor familiar blue skies and gentle seasons beneath the light of an alien sun. In 2014, Kepler 186f became the first Earth-sized planet confirmed to orbit within the habitable zone of its host star, marking a milestone in the search for potentially habitable worlds. Located 500 light-years away in the constellation Cygnus, this world receives 32% of the energy Earth gets from our Sun, placing it at the outer edge of its star's habitable zone, where liquid water could theoretically exist. The discovery required 4 years of Kepler observations, carefully analyzing the subtle dimming caused by planetary transits. Kepler 186f orbits a red dwarf star every 130 days, experiencing seasons that last about a third as long as Earth's. Computer models suggest this world could maintain stable surface temperatures if it possesses a substantial atmosphere with greenhouse gases. The planet likely experiences perpetual twilight compared to Earth, bathed in the reddish light of its smaller, cooler star. Scientists immediately began planning follow-up observations with larger telescopes, hoping to analyze the planet's atmosphere for signs of water vapor or oxygen. This distant cousin represents our best hope of finding a truly Earth-like world. What would it mean to discover that Earth's perfect twin exists, waiting patiently in the cosmic darkness? You're settling into the deepest quiet now, contemplating a world so dark it absorbs nearly all light that touches it. Darker than coal, darker than night itself. TARIS 2b, discovered in 2006, reflects less than 1% of the light that hits it, making it the darkest known planet in the universe. This gas giant, located 750 light-years away, appears blacker than charcoal, despite being heated to over 1,800 degrees Fahrenheit by its nearby star. The Transatlantic Exoplanet Survey detected this world through careful photometry, but its extreme darkness puzzled scientists for years. Most hot Jupiter planets reflect 10 to 15% of stellar light, appearing bright and cloud-covered. TARIS 2b breaks this pattern completely. Scientists believe its atmosphere contains light-absorbing compounds like vaporized sodium, potassium, and titanium oxide that trap incoming photons. The planet glows faintly red from its own internal heat, like a coal ember in cosmic darkness. This world challenges our understanding of planetary atmospheres, proving that not all worlds shine brightly under their stars. TARIS 2b exists as a cosmic void, a planetary shadow that swallows light. What other dark mysteries hide in the spaces between stars, absorbing light and secrets equally? You're wrapped in gentle contemplation now, pondering a world slowly dissolving into space as stellar gravity pulls it apart like cosmic taffy. WASP 121b orbits so close to its host star that powerful tidal forces are literally ripping the planet apart. Discovered in 2015, this hot Jupiter completes one orbit in just 1.3 days, racing around its star at breakneck speed. The planet's atmosphere reaches temperatures of 4,600 degrees Fahrenheit on the day side, hot enough to vaporize heavy metals like magnesium and iron. But WASP 121b's most striking feature is its teardrop shape, stretched by gravitational forces into an elongated form as stellar gravity tries to tear it apart. Hubble Space Telescope observations revealed that the planet is losing its atmosphere at an alarming rate, with hot gas streaming away into space like a comet's tail. Scientists discovered water vapor, along with glowing metals, being stripped from the planet's upper atmosphere. This world exists in a death spiral, slowly feeding its mass to the star that created it. WASP 121b represents the ultimate cosmic tragedy, a planet being devoured by its own sun. How do we comprehend worlds that exist in their final moments, slowly sacrificing themselves to stellar hunger? You're breathing in the cosmic quiet now, contemplating a world that endured the ultimate test, surviving inside its dying star and emerging as a diamond-hard survivor. Kepler 70b shouldn't exist. This planet orbits closer to its host star than any other known world, completing one revolution in just 5.76 hours. The extraordinary discovery emerged from Kepler data in 2011, revealing a planet that somehow survived being engulfed by its star during the red giant phase. When stars like our Sun exhaust their fuel, they expand into red giants, swallowing nearby planets. Kepler 70b was consumed by this stellar expansion, but miraculously survived inside the star's outer layers. As the dying star shed its outer envelope, the planet emerged, stripped down to its core and transformed into a scorched, rocky remnant. Surface temperatures now exceed 12,000 degrees Fahrenheit, making this world hotter than most stars' surfaces. The planet likely consists of crystallized carbon, essentially a diamond world forged in stellar fire. Scientists believe Kepler 70b represents what remains after the ultimate planetary catastrophe, a cosmic phoenix rising from stellar ashes. This survivor challenges everything we thought we knew about planetary endurance. What other impossible survivals await discovery in the cosmos, proving that destruction sometimes creates the most extraordinary worlds? You're nestled in sparkling wonder now, imagining a world where the ground beneath your feet would be made entirely of crystallized carbon worth more than entire nations. 55. Cancri E, discovered in 2004, captured imaginations worldwide when scientists realized this super-Earth might be composed largely of diamond. Located just 40 light-years away, this planet orbits so close to its sun-like star that it completes one revolution in 18 hours. The world receives intense stellar radiation, creating surface temperatures exceeding 3,900 degrees Fahrenheit. Spitzer Space Telescope observations revealed that 55 Cancri E has twice Earth's radius, but 8 times its mass, suggesting a composition unlike any planet in our solar system. Scientists calculated that the planet's high carbon-to-oxygen ratio could create conditions where carbon crystallizes into diamond under extreme pressure and heat. If confirmed, this world would contain more diamond than the total value of Earth's entire economy. The planet likely has no atmosphere, existing as a scorched ball of crystallized carbon orbiting under the blazing light of its star. Yet recent studies suggest the world might have a thin atmosphere and even lava flows, complicating the diamond planet hypothesis. What would it mean to discover that the most precious substance on Earth is common building material on distant worlds? You're drifting into binary tranquility now, contemplating a world that watches 2 suns dance in its sky, just like the fictional Tatooine from our dreams. In 2011, Kepler 16b became the first planet confirmed to orbit 2 stars simultaneously, turning science fiction into scientific fact. This Saturn-sized world, located 200 light-years away, orbits both members of a binary star system every 627 days. The discovery required extraordinary patience, as astronomers analyzed complex light curves showing eclipses between the 2 stars, and additional dimming when the planet transited both. The gravitational dynamics of a 3-body system create orbital instabilities that most scientists thought would prevent planet formation. Yet Kepler 16b exists in stable orbit, proving that binary star systems can nurture planetary companions. The world likely experiences double sunrises and sunsets, with complex seasonal patterns as it orbits around both stellar parents. However, unlike the warm desert world of Tatooine, Kepler 16b remains a cold gas giant, too distant from its stars to support liquid water. The planet's existence opened new possibilities for planetary formation, suggesting that binary star systems, which comprise half of all stars, might commonly host planets. Why does reality consistently exceed the boundaries of our most creative fictional imaginings? You're settled in crystalline contemplation now, pondering a world made entirely of diamond that orbits the remnant of a once mighty star in eternal, glittering silence. PSR JSMC 190438b represents one of the strangest objects in the cosmos, a planet composed entirely of crystallized carbon orbiting a rapidly spinning neutron star. Discovered in 2011 through radio pulsar timing, this world formed from the compressed remnant of a white dwarf star that was slowly consumed by its neutron star companion. The intense gravitational field compressed the white dwarf's carbon and oxygen into a super-dense diamond sphere about 5 times Earth's mass, but only slightly larger than Jupiter. This diamond planet orbits its pulsar every 2.2 hours, experiencing gravitational forces so intense that a sugar cube-sized piece would weigh as much as a mountain. The neutron star spins 173 times per second, sweeping beams of radiation across space like a cosmic lighthouse. Radio telescopes detected this system by measuring the precise timing of pulsar flashes, noticing minute variations caused by the planet's gravitational influence. This world exists in conditions impossible to imagine. A diamond bigger than Earth, forged in stellar death, orbiting a star compressed to city size. What other impossible treasures hide in the graveyards of dead stars, waiting to be discovered by patient observers? You're breathing in stellar serenity now, contemplating a world that bleeds helium into space, slowly dissolving like a cosmic soap bubble under its star's relentless heat. KOI 55b, also known as Kepler 70b, orbits closer to its host star than any other confirmed planet, completing one revolution in less than 6 hours. This remnant world, discovered in 2011, likely represents the stripped core of a former gas giant that lost its hydrogen and helium atmosphere to stellar radiation. The planet now consists primarily of heavier elements like carbon and oxygen, but traces of helium still escape into space, creating a tenuous atmosphere that continuously evaporates. Surface temperatures exceed 12,000 degrees Fahrenheit, making this world hotter than many stellar surfaces. The host star, KOI 55, recently evolved beyond the red giant phase, suggesting this planet survived being engulfed during its star's expansion. Scientists believe KOI 55b once possessed a substantial helium atmosphere, but proximity to its star strips away atmospheric particles through thermal escape and stellar wind interaction. This world exists in a perpetual state of atmospheric loss, slowly revealing its rocky core as lighter elements disappear into space. The planet serves as a laboratory for studying atmospheric evolution under extreme conditions. How many worlds are quietly disappearing into space, leaving only their cores as monuments to cosmic violence? You're wrapped in visual wonder now, contemplating the first planet beyond our solar system that humans could actually see with their own eyes through a telescope. HR 8799b made history in 2008 as one of the first exoplanets directly photographed rather than detected through indirect methods. Located 129 light-years away, this gas giant orbits its young host star at a distance equivalent to Pluto's orbit around our Sun. The Keck and Gemini observatories captured actual images of this world using coronagraphic techniques to block the star's overwhelming light. HR 8799b appears as a faint infrared dot, glowing with heat from its own formation just 60 million years ago. This planet, along with 3 companions in the same system, represents a rare glimpse of planetary formation in action. The world contains 7 times Jupiter's mass and maintains surface temperatures around 1,800 degrees Fahrenheit from residual heat of gravitational collapse. Spectroscopic analysis revealed water vapor, carbon monoxide, and methane in its atmosphere. The direct detection marked a revolution in exoplanet science, proving that we could not only infer the existence of distant worlds but actually observe them. HR 8799b became the first exoplanet portrait in humanity's cosmic photo album. What does it mean to finally see worlds that were once invisible, transforming theoretical points into actual places? You're settling into hopeful tranquility now, contemplating one of the most Earth-like worlds ever discovered, a recent find that reignited dreams of cosmic neighbors. In 2020, scientists analyzing archived Kepler data discovered Kepler 1649c, an Earth-sized planet orbiting within its red dwarf star's habitable zone. Initially overlooked by computer algorithms, this world emerged from careful human review of discarded data, proving that sometimes our most significant discoveries hide in plain sight. Located 301 light-years away, Kepler 1649c receives 75% of the energy Earth gets from our Sun, placing it in the sweet spot where liquid water could exist on its surface. The planet's size matches Earth within 6%, making it one of the closest analogs to our home world ever found. The discovery required painstaking analysis of transit data, measuring the minute dimming when the planet passes between us and its star. Kepler 1649c orbits a red dwarf every 19.5 Earth days, likely experiencing tidal locking where one hemisphere faces permanent day while the other endures eternal night. Yet the twilight zone between these extremes might maintain temperate conditions suitable for life. This world represents our latest hope for finding a truly habitable exoplanet. Why do our most promising discoveries often emerge from data we initially dismissed as unimportant? You're drifting into cosmic curiosity now, pondering a naked planetary core that lost everything except its heart, revealing the hidden anatomy of world formation. TOI 849b, discovered by NASA's TESS mission in 2020, represents something unprecedented: the exposed core of what was once a massive gas giant. This Neptune-sized world orbits extremely close to its host star, completing one revolution in just 18 hours, while maintaining a density similar to Earth despite being much larger. Scientists believe TOI 849b originally formed as a gas giant similar to Jupiter, but stellar radiation stripped away its entire hydrogen and helium atmosphere over millions of years. What remains is the rocky, icy core that once lay hidden beneath thousands of miles of gas. The discovery process involved months of follow-up observations with ground-based telescopes, measuring the planet's mass through radial velocity techniques. This world provides an unprecedented view into planetary interiors, revealing the solid foundation that underlies all gas giant planets. TOI 849b likely contains more rock and ice than any planet in our solar system, compressed into a sphere that would fit between Earth and Neptune. The planet serves as a cosmic dissection, showing us what lies beneath the atmospheric layers of distant worlds. Hey friends, if you love this series exploring cosmic mysteries, don't forget to subscribe for more celestial bedtime stories. What other planetary secrets lie hidden beneath the atmospheric veils of distant worlds, waiting to be exposed by stellar winds? You're settling into gentle anticipation now, contemplating one of the closest potentially habitable worlds to Earth, a cosmic neighbor hiding just beyond our solar system's edge. Wolf 1061e orbits a red dwarf star just 13.8 light-years from Earth, making it one of the nearest potentially habitable exoplanets ever discovered. Found in 2015 through radial velocity measurements, this super-Earth receives stellar energy similar to Venus, placing it at the inner edge of its star's habitable zone. The planet completes one orbit every 17.9 days, likely experiencing tidal locking, where one hemisphere faces permanent day while the other endures eternal night. Australian astronomers spent years analyzing tiny wobbles in the host star's motion, detecting the gravitational pull of 3 planets in this nearby system. Wolf 1061c became an immediate target for follow-up studies due to its proximity and potential habitability. Scientists believe this world might maintain liquid water in its twilight zone, the boundary between scorching day and frozen night sides. The discovery sparked discussions about future interstellar missions, as Wolf 1061c represents one of the most realistic targets for humanity's first steps beyond our solar system. What would it mean to know that a potentially habitable world waits just a few dozen light-years away? You're wrapped in cosmic wonder now, pondering a massive planet that shouldn't exist according to our theories, orbiting a star too small to have created it. NGTS-1b challenged fundamental assumptions about planet formation when discovered in 2017. This gas giant, similar in size to Jupiter, orbits a red dwarf star only half the mass of our Sun. According to standard planetary formation models, such small stars shouldn't possess enough material in their protoplanetary disks to create massive gas giants. The Next Generation Transit Survey detected this anomaly through careful monitoring of stellar brightness, observing the regular dimming caused by planetary transits. NGTS-1b completes one orbit every 2.6 days, racing around its diminutive host star at incredible speed. The planet's existence forced astronomers to reconsider how giant planets form around low-mass stars. Some theories suggest NGTS-1b migrated inward from the outer reaches of its stellar system, while others propose that red dwarf disks contain more material than previously thought. This world serves as a cosmic puzzle piece that doesn't fit our current understanding of planetary system architecture. The discovery opened new questions about what types of planets can exist around the universe's most common stars. Why do the most groundbreaking discoveries consistently emerge from worlds that break our carefully constructed rules? You're drifting into dusty tranquility now, contemplating a young world swimming through clouds of cosmic debris from its system's violent formation. IU Microscopy B, discovered by NASA's TESS mission in 2020, orbits a young red dwarf star surrounded by one of the most prominent debris disks known to astronomy. This Neptune-sized planet, located just 32 light-years away, provides a rare glimpse into planetary formation in action. The host star, only 23 million years old, still bears the chaotic remnants of its birth. Vast clouds of dust and rocky fragments left over from planet-building processes. AU Mike B completes one orbit every 8.5 days, plowing through this debris field like a cosmic snowplow. The planet's discovery required careful analysis of test data, separating the planetary transit signal from stellar activity and dust interactions. Scientists observe this system as a laboratory for understanding how planets form and migrate within dusty protoplanetary environments. The young star frequently flares, bombarding its planet with intense radiation that may strip away atmospheric material. This world exists in the turbulent adolescence of a planetary system, still shaped by the violent forces that gave it birth. What stories of formation and survival are written in the dust clouds surrounding distant stars? You're nestled in impossible contemplation now, pondering a planet that exists where no planet should survive, in the cosmic wasteland known as the Neptune Desert. LTT 9779b occupies the Neptune Desert, a region around stars where planets of Neptune's size simply don't exist. Discovered by NASA's TESS in 2020, this ultra-hot Neptune completes one orbit in just 19 hours, while maintaining its atmospheric envelope despite receiving 170 times more stellar energy than Earth. The planet shouldn't exist according to current theories. Such intense stellar radiation should strip away the atmospheres of mid-sized planets, leaving only rocky cores or gas giants. LTT 9779b defies these expectations, somehow retaining a substantial atmosphere of hydrogen and helium. The discovery required follow-up observations with ground-based telescopes to confirm the planet's unusual properties. Scientists believe this world might have migrated to its current position relatively recently, before stellar winds could completely strip its atmosphere. Alternatively, the planet might possess an unusually strong magnetic field that deflects stellar radiation. This cosmic anomaly forces us to reconsider atmospheric retention around ultra-hot planets and the mechanisms that create the Neptune Desert. What other impossible survivors lurk in the cosmic wastelands where planets shouldn't exist? You're breathing in metallic serenity now, imagining storms where liquid iron falls from alien skies like glowing tears from a cosmic furnace. WASP-76b experiences weather unlike anywhere else in the known universe. It literally rains molten iron. Discovered in 2013, this ultra-hot Jupiter orbits so close to its host star that it completes one revolution in 1.8 days. Dayside temperatures reach 4,350 degrees Fahrenheit, hot enough to vaporize metals like iron and magnesium. The European Southern Observatory's Very Large Telescope revealed this planet's extraordinary meteorology through high-resolution spectroscopy. On the scorching day side, iron exists as vapor, carried by supersonic winds to the cooler night side where temperatures drop just enough for the metal to condense into liquid droplets. These iron raindrops fall through the planet's atmosphere like metallic precipitation, potentially pooling in vast molten lakes on the night side. The planet shows extreme day-night temperature differences, with the day side glowing white-hot while the night side remains relatively cool. WASP 76b challenges our understanding of atmospheric dynamics on ultra-hot planets, where familiar elements behave in completely alien ways. What other impossible weathers await discovery on worlds where the very air burns with stellar fire? You're settling into neighborhood wonder now, contemplating a scorching world in our cosmic backyard that might once have harbored the ingredients for life. GJ 357b orbits one of the nearest red dwarf stars to Earth, located just 31 light-years away in the constellation Hydra, discovered by NASA's TESS in 2019. This planet receives 11 times more energy from its star than Earth gets from our Sun, making it too hot for liquid water despite its Earth-like size. The world completes one orbit every 3.9 days, likely maintaining surface temperatures around 490 degrees Fahrenheit. Scientists analyzing TESS data found 2 additional planets in this system, including one that might be habitable. GJ 357b serves as Earth's scorched twin, similar in size and composition, but baked by its proximity to its parent star. The planet likely lost any atmosphere it once possessed due to intense stellar radiation, leaving a bare rocky surface. Ground-based telescopes confirmed the planet's properties through radial velocity measurements, precisely determining its mass and density. This nearby world provides an excellent target for atmospheric studies with future space telescopes, potentially revealing clues about rocky planet evolution around red dwarf stars. How many Earth-sized worlds in our cosmic neighborhood tell stories of what our planet might have become? You're wrapped in molten contemplation now, pondering a world where oceans of liquid rock flow beneath skies torn by winds faster than sound itself. K2-141b represents one of the most extreme rocky planets ever discovered, a world where the very ground flows like water. Found by NASA's K2 mission in 2020, this super-Earth orbits so close to its host star that it maintains permanent magma oceans on its day side. Surface temperatures exceed 5,400 degrees Fahrenheit, hot enough to vaporize rock and create an atmosphere of silicate vapor. The planet likely shows extreme tidal locking, with a molten day side and a solid night side connected by supersonic winds reaching 3,100 mph. These winds carry vaporized rock from the day side to the night side, where it condenses and falls as silicate snow before flowing back as molten rivers. Scientists used computer models to predict this world's extraordinary weather patterns, revealing a rock cycle unlike anything on Earth. The planet's surface resembles a hellish version of our world's water cycle, with evaporation, precipitation, and flow all occurring with liquid rock instead of water. K2-1041b provides insights into the most extreme conditions under which rocky planets can exist. What other alien versions of familiar processes await discovery on worlds that push the boundaries of physics? You're drifting into harmonic serenity now, contemplating a stellar system where 6 planets dance in perfect mathematical rhythm like a cosmic symphony. The Tau I-178 system, discovered by NASA's TESS in 2021, contains 6 planets locked in a rare chain of orbital resonances, creating a gravitational ballet of unprecedented complexity. Located 200 light-years away, 5 of these worlds orbit in a precise 18.9643 ratio, meaning their orbital periods align in mathematical harmony. The European Space Agency's Cheops mission confirmed this extraordinary arrangement through careful transit timing analysis. Such resonant chains form when planets migrate inward through their protoplanetary disk while maintaining gravitational synchronization. The discovery required months of precise observations to untangle the complex pattern of planetary transits. Scientists believe this system preserved its original architecture from formation. Unlike our solar system, where planetary migrations disrupted early resonances, the innermost planet, TOI 178b, completes one orbit in just 1.9 days, while the outermost takes 20.7 days. This cosmic choir demonstrates how gravity can create order from chaos, sculpting planetary systems into configurations of mathematical beauty. The system serves as a laboratory for studying planetary formation and migration processes. What cosmic music plays in the gravitational harmonies between distant worlds dancing in perfect synchronization? You're nestled in orbital melancholy now, contemplating a world caught in an inevitable death spiral, slowly surrendering itself to stellar embrace. Kepler 16558b holds the distinction of being the first planet discovered to be spiraling into its host star due to tidal decay. Initially discovered by Kepler in 2019, this hot Jupiter completes one orbit in just 3.8 days, while gradually moving closer to its stellar parent. The planet's fate was sealed by tidal forces. As it orbits, gravitational interactions with its star cause orbital energy to dissipate, slowly shrinking the orbit. Scientists calculated that Kepler 1658b loses about 131 milliseconds from its orbital period every year, a cosmic countdown to eventual destruction. The discovery emerged from careful analysis of Kepler data spanning nearly a decade, revealing the gradual orbital decay through precise transit timing measurements. This world provides the first observational evidence of tidal orbital decay around a main sequence star, confirming theoretical predictions about planetary death spirals. The planet likely has only a few million years remaining before stellar tidal forces tear it apart completely. Kepler 1658b serves as a preview of planetary endings, showing us how worlds die not with explosive violence, but through slow gravitational surrender. What other cosmic endings play out in slow motion across the vast timescales of stellar evolution? You're breathing in systematic wonder now, contemplating a nearby stellar family where 3 rocky worlds might tell the story of planetary formation and evolution. The L98-59 system, located just 35 light-years away, hosts at least 3 confirmed super-Earth planets discovered by NASA's TESS in 2019. This red dwarf system became a prime target for atmospheric studies due to its proximity and the favorable sizes of its planets for transmission spectroscopy. The innermost world, L98-59b, takes just 2.25 days to orbit its star and receives intense stellar radiation. The middle planet completes one orbit in 3.7 days, while the outermost confirmed world takes 7.5 days. Ground-based telescopes measured the planet's masses through radial velocity observations, revealing densities consistent with rocky compositions. Scientists believe additional planets might exist in this system's outer regions, potentially including worlds in the habitable zone. The system's youth and proximity make it an ideal laboratory for studying atmospheric retention around red dwarf stars. Future observations with the James Webb Space Telescope might detect water vapor or other atmospheric components in these worlds. L98-59 represents our closest opportunity to study multiple rocky planets around a single star, providing insights into how Earth-sized worlds form and evolve. What stories of planetary birth and evolution are written in the orbital architecture of nearby stellar systems? You're settling into blazing tranquility now, contemplating a world hotter than most stars, where the very atoms in its atmosphere break apart under unimaginable heat. KLT 9b, discovered in 2016, holds the record as the hottest known exoplanet, with dayside temperatures reaching 7,800 degrees Fahrenheit, hotter than the surface of our Sun. This ultra-hot Jupiter orbits a massive A-type star every 1.5 days, tidally locked in perpetual scorching daylight. The Kilodegree Extremely Little Telescope survey detected this world through careful monitoring of stellar brightness variations. At such extreme temperatures, hydrogen molecules in the planet's atmosphere dissociate into individual atoms, while heavier elements like iron and titanium exist as gas. The intense stellar radiation constantly strips away the planet's atmosphere, creating a comet-like tail of escaping material. Scientists studying KELT 9b discovered that it's slowly evaporating, losing mass at a rate that will eventually leave only a rocky core. The planet's night side remains cooler at around 4,600 degrees Fahrenheit, creating extreme temperature gradients that drive supersonic winds. This world exists at the absolute limit of planetary survival, a cosmic furnace that challenges our understanding of how planets can endure. What other worlds push the boundaries of existence in the space between planet and star? You're wrapped in crystalline clarity now, pondering a world with perfectly transparent skies that reveal the secrets of atmospheric composition to distant observers. WASP 996b became famous as one of the first exoplanets with a completely cloudless atmosphere, allowing astronomers to peer deep into its gaseous envelope. Discovered in 2013, this hot Jupiter orbits its Sun-like star every 3.4 days at a distance closer than Mercury. The wide angle. Search for Planets survey initially detected this world through transit photometry, but follow-up spectroscopic observations revealed its most remarkable feature: pristine atmospheric transparency. Most hot Jupiter atmospheres contain clouds and hazes that obscure their chemical composition, but WASP 96b's extreme heat prevents cloud formation entirely. The Hubble Space Telescope detected clear signatures of water vapor in the planet's atmosphere, along with traces of sodium. In 2022, the James Webb Space Telescope produced the most detailed atmospheric spectrum ever obtained from an exoplanet, revealing water, clouds, and hazes with unprecedented precision. This world serves as an ideal laboratory for atmospheric studies, its clear skies offering a window into the chemical processes occurring in hot giant planet atmospheres across the galaxy. Why do the clearest atmospheric windows often open on the most inhospitable worlds? You're drifting into eccentric serenity now, contemplating a world that experiences the most extreme seasonal variations imaginable as it follows a wildly elliptical orbit. HD 80606b travels one of the most eccentric orbits known among exoplanets, swinging from distances similar to Earth's orbit to within 4 stellar radii of its host star. Discovered in 2001, this gas giant takes 111 days to complete one highly elliptical journey around its Sun-like star. During closest approach, the planet receives 825 times more energy than at its farthest point, creating temperature swings from 1,800 to 2,200 degrees Fahrenheit in just 6 hours. The McDonald Observatory detected this world through radial velocity measurements, tracking the star's motion as the planet's gravity tugs it back and forth. Spitzer Space Telescope observations revealed the planet's rapid heating during periastron passage, watching its day-side temperature climb in real time as it approaches its star, HD 80606b, likely formed in a circular orbit before gravitational interactions with its binary companion star stretched its path into the current extreme ellipse. This world experiences seasons of unimaginable intensity, alternately freezing and roasting as it races through its elongated orbit. What stories of cosmic violence are written in the eccentric orbits of distant worlds? You're nestled in paradoxical wonder now, contemplating a world made of ice that burns at 800 degrees Fahrenheit, defying every earthly understanding of matter. Gliese 436b exists in a state that seems physically impossible, a planet composed largely of water ice that maintains surface temperatures hot enough to melt copper. Discovered in 2004 around a nearby red dwarf star, this Neptune-sized world orbits every 2.6 days at a distance where water should exist only as superheated steam. The planet's extraordinary nature emerged from precise mass and radius measurements, revealing a density consistent with substantial water content. Under the intense pressure created by the planet's mass, water molecules compress into exotic forms of ice that remain solid despite scorching temperatures. These hot ice phases, including Ice 7 and Ice X, exist nowhere naturally on Earth but dominate Gliese 436b's interior. The planet likely possesses a hydrogen-helium atmosphere above its burning ice mantle, creating a world where familiar substances behave in completely alien ways. Spitzer Space Telescope observations confirmed the planet's unusual thermal properties, measuring infrared emissions from this cosmic contradiction. Gliese 436b challenges our understanding of planetary composition and the behavior of matter under extreme conditions. How many other impossible states of matter await discovery in the extreme environments of distant worlds? You're breathing in stellar serenity now, contemplating a bloated world being slowly sculpted by the relentless winds from its young active parent star. Coro T2b orbits one of the most magnetically active stars known to host planets, enduring constant bombardment from powerful stellar winds and flares. Discovered by the French Coro T mission in 2007, this gas giant maintains an unusually large radius despite relatively low mass, suggesting ongoing atmospheric heating from its star's energetic output. The host star, Coro T2, displays magnetic activity levels hundreds of times stronger than our Sun, generating frequent X-ray flares and powerful stellar winds. These stellar outbursts continuously inflate the planet's atmosphere, preventing normal gravitational contraction and creating a world with the density of styrofoam. Scientists studying this system discovered that stellar activity can dramatically affect planetary structure, puffing up atmospheric envelopes far beyond normal limits. The planet completes one orbit every 1.7 days, remaining perpetually bathed in its star's violent magnetic field. Coro T2b serves as a laboratory for studying star-planet interactions, showing how stellar youth and activity can reshape planetary architecture. This relationship between star and planet continues to evolve as the host star gradually calms with age. What other cosmic relationships between stars and planets are still being written in stellar fire and planetary response? You're settling into gravitational contemplation now, pondering a massive world that defies expectations by maintaining extraordinary density while following a mysteriously tilted orbital path. Hat P2b challenges conventional wisdom about gas giant composition and formation. Discovered in 2007, this planet contains 8 times Jupiter's mass, compressed into a volume only slightly larger, creating one of the densest gas giants known. The Hungarian-made automated telescope network detected this world through transit observations, but follow-up studies revealed its most puzzling characteristic: an orbital inclination of 9 degrees relative to its star's equator. Most planets form from protoplanetary disks aligned with their star's rotation, making HAT P2b's tilted orbit a cosmic mystery. The planet's exceptional density suggests a core containing 60 to 70 Earth masses of heavy elements, far more than standard formation models predict. Some theories propose that HAT P2b formed through the collision and merger of smaller planets, explaining both its high density and unusual orbital inclination. The world completes one orbit every 5.6 days around its F-type star, maintaining stable temperatures around 2,000 degrees Fahrenheit. This planetary giant serves as evidence that planet formation can proceed through pathways far more violent and complex than once imagined. What other cosmic collisions and mergers have sculpted the strange worlds that populate distant stellar systems? You're wrapped in inevitable tranquility now, contemplating a world racing toward its stellar doom, destined to be consumed by the very star that gave it light. WASP 18b faces an inescapable fate: collision with its host star within 1 million years, a cosmic blink of an eye. Discovered in 2009, this massive hot Jupiter contains 10 times Jupiter's mass while orbiting its star every 23 hours, one of the shortest orbital periods known. The planet's extreme proximity creates powerful tidal forces that gradually drain orbital energy, causing the world to spiral inward toward destruction. The Super WASP survey detected this doomed world through transit photometry, but its discovery posed immediate puzzles about planetary survival. Tidal interactions between WASP 18b and its star should have already caused the planet's destruction, yet it somehow persists in stable orbit. Some theories suggest the planet arrived at its current position relatively recently through orbital migration, while others propose unknown mechanisms that temporarily halt tidal decay. The world's surface temperature exceeds 4,000 degrees Fahrenheit, hot enough to vaporize most materials. WASP 18b serves as a preview of planetary death, showing us how worlds meet their end, not through explosive violence, but gradual gravitational surrender. What cosmic stories of inevitability play out as worlds slowly spiral toward their stellar graves? You're nestled in miniature wonder now, contemplating the tiniest world ever discovered beyond our solar system, smaller than Earth's moon, yet orbiting a distant star. Kepler 37b holds the record as the smallest confirmed exoplanet, with a radius just 20% larger than Earth's moon. Discovered by NASA's Kepler mission in 2013, this diminutive world orbits a sun-like star every 13 days, alongside 2 larger planetary companions. The detection required extraordinary precision in photometry, measuring brightness variations of just 0.001% as the tiny planet transited its star. Kepler 37b likely lacks any substantial atmosphere due to its small size and proximity to its host star, existing as a bare, rocky world scorched by stellar radiation. Surface temperatures probably exceed 800 degrees Fahrenheit, creating conditions similar to Mercury but on a much smaller scale. The planet's discovery pushed the boundaries of transit detection techniques, proving that space-based telescopes could find worlds smaller than any in our outer solar system. Scientists believe Kepler 37b represents a class of subterrestrial planets that may be common throughout the galaxy, but remain difficult to detect from Earth. This tiny world challenges assumptions about minimum planetary sizes and the lower limits of planet formation processes. What other miniature worlds hide in the data, too small to notice but large enough to harbor cosmic secrets? You're drifting into distorted serenity now, contemplating a world so close to its star that tidal forces have stretched it into the shape of a cosmic donut. WASP-12b exists in a state of extreme gravitational distress, stretched into an egg-like shape by powerful tidal forces from its nearby star. Discovered in 2008, this hot Jupiter orbits so close to its host star that it completes one revolution in just 26 hours. The planet's proximity creates tidal bulges so extreme that its shape resembles a football rather than a sphere. Stellar gravity pulls the planet's atmosphere into long streamers that flow toward the star like cosmic rivers. Hubble Space Telescope observations revealed that WASP-12b is slowly being consumed by its star, losing atmospheric mass at a rate of 10 billion tons per second. The planet's dayside temperature reaches 4,600 degrees Fahrenheit, hot enough to dissociate water molecules and create clouds of exotic compounds. Carbon monoxide, which normally burns in oxygen, remains stable in the planet's oxygen-poor atmosphere. WASP-12b demonstrates the extreme plasticity of planetary bodies under intense gravitational stress, showing how worlds can be sculpted into impossible shapes by stellar forces. How many other cosmic sculptures are being carved by gravity's invisible hand in the space between stars and planets? You're settling into barren contemplation now, pondering a naked, rocky world that lost its atmosphere to stellar winds, leaving only bare stone under alien skies. LHS 3844b represents the ultimate minimalist planet, a rocky world completely stripped of its atmosphere by relentless stellar radiation. Discovered by NASA's TESS in 2018, this super-Earth orbits a nearby red dwarf star every 11 hours, tidally locked with one hemisphere facing permanent day. Spitzer Space Telescope observations revealed the planet's most striking characteristic: virtually no atmosphere whatsoever. The day side reaches temperatures around 1,300 degrees Fahrenheit, while the night side plunges to near absolute zero, with no atmospheric circulation to moderate these extremes. The stark temperature difference between hemispheres confirmed the absence of any substantial gaseous envelope that might redistribute heat. Scientists believe LHS 3844b once possessed an atmosphere but lost it to photoevaporation from its active host star. The planet likely consists of bare rock and metal, possibly covered with a thin layer of condensed materials on the frigid night side. This world serves as an extreme example of atmospheric loss, showing how red dwarf planets can be stripped down to their rocky cores. LHS 3844b provides insights into the ultimate fate of rocky planets around the galaxy's most common stars. What other stripped worlds orbit red dwarf stars, reduced to their bare essence by stellar fire? You're settling into gravitational uncertainty now, contemplating a world so massive it blurs the line between planet and failed star, existing in cosmic limbo. XO3b challenges our definition of what constitutes a planet. Discovered in 2007, this object contains 13 times Jupiter's mass, just below the threshold where nuclear fusion begins and brown dwarfs are born. The XO project detected this massive world through transit photometry, but its nature sparked immediate debates. At such high mass, XO3b likely generates heat through gravitational contraction rather than stellar heating alone. The object orbits its host star every 3.2 days, maintaining a surprisingly circular orbit despite its extreme mass. Scientists remain divided on whether to classify XO3b as a supermassive planet or a failed star that never quite ignited fusion. This world exists at the boundary between planetary and stellar physics, a reminder that nature doesn't always fit our neat categories. Where do we draw the lines between planets, brown dwarfs, and stars in the cosmic continuum of mass and energy? You're wrapped in aquatic serenity now, contemplating a world that might harbor vast oceans in the most famous multi-planet system beyond our solar system. TRAPPIST-1d orbits within the habitable zone of its ultra-cool red dwarf star, one of 7 Earth-sized worlds in this remarkable system just 40 light-years away. Discovered through ground-based telescopes in 2016, this planet receives about the same amount of energy as Mars gets from our Sun. Computer models suggest TRAPPIST-1d could maintain liquid water on its surface if it possesses a substantial atmosphere with greenhouse gases. The planet likely experiences extreme tidal locking, with one hemisphere facing permanent day while the other endures eternal night. Yet, between these extremes might exist a temperate twilight zone where water could remain liquid year-round. The world completes one orbit every 4.05 days, locked in gravitational resonance with its 6 planetary siblings. Scientists believe this system formed much closer to its star before migrating outward, preserving the delicate orbital harmony we observe today. Scientists believe this system formed much closer to its star before migrating outward, preserving the delicate orbital harmony we observe today. What stories of migration and survival are written in the perfect gravitational dance of 7 worlds? You're drifting into peaceful proximity now, pondering one of the closest potentially habitable worlds orbiting the most tranquil star in our cosmic neighborhood. Ross 128 b orbits a red dwarf star just 11 light-years from Earth, making it one of our nearest potentially habitable neighbors. Discovered in 2017 through radial velocity measurements, this temperate world receives 38% more energy than Earth, but orbits a remarkably quiet star. Unlike most red dwarfs, Ross 128 shows minimal flare activity, creating stable conditions that might allow atmospheric retention over billions of years. The planet completes one orbit every 9.9 days, likely tidally locked, but potentially maintaining moderate temperatures in its twilight regions. European Southern Observatory astronomers spent years tracking tiny wobbles in the host star's motion to confirm this world's existence. Ross 128b represents our best hope for finding a truly Earth-like atmosphere around a red dwarf star. The system's proximity makes it an ideal target for future atmospheric studies and possibly humanity's first serious attempt at interstellar exploration. Why do the most promising worlds for life often orbit the galaxy's smallest and most common stars? You're nestled in meteorological chaos now, contemplating a world where winds exceed hurricane force and day-night temperature differences create perpetual storms. WASP-43b completes one orbit around its host star in just 19 hours, making it one of the fastest orbiting planets known. Discovered in 2011, this hot Jupiter experiences extreme day-night temperature variations that drive winds reaching 5,000 mph. The SuperWASP survey detected this world through transit observations, but follow-up studies revealed its extraordinary atmospheric dynamics. Spitzer Space Telescope mapped the planet's thermal emissions, discovering temperature differences of 1,500 degrees Fahrenheit between day and night sides. These extreme gradients create permanent storm systems that circulate around the globe like cosmic hurricanes. The planet's rapid orbit and close proximity to its star generate powerful tidal forces that keep its interior molten despite its gaseous nature. Scientists studying WASP-43b have created detailed weather maps of its atmosphere, revealing how heat transport works on worlds with extreme stellar irradiation. What other meteorological mysteries await discovery on worlds where weather systems span entire hemispheres? You're breathing in interstellar cold now, contemplating a frozen world orbiting our second closest stellar neighbor in the lonely darkness beyond the habitable zone. Barnard's Star B became one of the most significant exoplanet discoveries when confirmed in 2018, orbiting the nearest single star to our solar system at just 6 light-years away. This super-Earth containing at least 3.2 times our planet's mass, takes 233 days to orbit its ancient red dwarf host star. Despite its proximity to Earth, Barnard's star B receives minimal stellar energy, maintaining surface temperatures around 270 degrees Fahrenheit. European astronomers spent decades analyzing radial velocity data to detect this world's subtle gravitational influence on its parent star. The planet likely resembles a frozen version of Earth, possibly retaining a thin atmosphere and subsurface liquid water heated by radioactive decay. Barnard's star itself is over 10 billion years old, twice the age of our solar system, making any planet's ancient worlds that have endured cosmic winter for eons. This nearby frozen world represents our closest glimpse of planetary evolution around the galaxy's oldest stars. What ancient secrets might lie frozen in the oldest planetary systems in our cosmic neighborhood? You're settling into atmospheric wonder now, contemplating the first Neptune-sized world where astronomers detected familiar water vapor clouds drifting through alien skies. JT-P11b made history as the first Neptune-sized exoplanet where astronomers successfully detected water vapor in its atmosphere. Discovered in 2009, this warm Neptune orbits a sun-like star every 4.9 days, while maintaining a clear, cloud-free atmosphere in its upper regions. The Hungarian Automated Telescope Network initially found this world through transit observations, but Hubble Space Telescope spectroscopy revealed its water signature years later. Unlike larger gas giants, where thick clouds often obscure atmospheric composition, HAT-P11b's smaller size allows deeper penetration of starlight through its gaseous envelope. Scientists detected not only water vapor, but also clear evidence of atmospheric hazes at high altitudes. The planet's atmosphere shows signs of strong stellar wind interactions, possibly stripping lighter elements while preserving heavier molecules like water. HAT-P11b bridges the gap between terrestrial and gas giant atmospheres, offering insights into how mid-sized planets retain and modify their gaseous envelopes. What other familiar molecules drift through the alien atmospheres of distant Neptune-like worlds? You're wrapped in gravitational partnership now, contemplating the first confirmed exomoon discovery, a satellite world orbiting a distant gas giant. Kepler 1625b represents humanity's first confirmed detection of a moon orbiting an exoplanet, opening entirely new frontiers in planetary system architecture. The host planet, Kepler 1625b, is a gas giant similar to Jupiter, located 8,000 light-years away in the constellation Cygnus. Astronomers analyzing Kepler data noticed subtle anomalies in the planet's transit timing and depth, suggesting the gravitational influence of a large satellite. Follow-up observations with Hubble Space Telescope in 2017 confirmed the moon's existence through additional transit variations. This exomoon likely measures similar to Neptune in size, making it larger than any moon in our solar system. The discovery required extraordinary precision, detecting brightness changes of less than 0.01% as both planet and moon crossed their host star. Kepler 1625b orbits its parent planet at a distance similar to our moon's orbit around Earth, but its massive size suggests a violent formation history involving planetary collisions or capture events. What other satellite worlds await discovery in the gravitational embrace of distant gas giants? You're drifting into spectroscopic serenity now, contemplating a bloated world whose atmosphere has been dissected by telescopes, revealing the chemical fingerprints of distant weather. WASP-39b became one of the most thoroughly studied exoplanet atmospheres, revealing unprecedented details about chemical processes on distant worlds. Discovered in 2011, This hot Jupiter maintains an unusually low density while orbiting its host star every 4.1 days. The Super WASP survey initially detected this world, but multiple space telescopes have since analyzed its atmospheric composition. Hubble revealed water vapor and sodium, while Spitzer detected carbon monoxide and dioxide. The James Webb Space Telescope produced the most detailed atmospheric spectrum ever obtained, identifying sulfur dioxide for the first time in an exoplanet atmosphere. WASP-39b's puffy nature allows starlight to penetrate deep into its gaseous envelope, making it an ideal laboratory for atmospheric studies. Scientists discovered that the planet's atmosphere contains more heavy elements than expected, suggesting formation through planetesimal accretion rather than gas capture alone. What other atmospheric libraries await reading in the starlight filtered through distant planetary skies? You're nestled in cosmic nursery wonder now, contemplating one of the youngest planets ever discovered, still glowing with the heat of recent formation. K233b offers a rare glimpse into planetary infancy, orbiting a star system only 5 to 10 million years old. Discovered by NASA's K2 mission in 2016, this Neptune-sized world represents one of the youngest planets ever found, existing when our solar system was still forming from primordial dust and gas. The host star belongs to the Upper Scorpius Association, a nearby stellar nursery where planets are actively coalescing from protoplanetary disks. K233b completes one orbit every 5.4 days, suggesting it formed close to its star or migrated inward during its youth. The planet likely still glows with residual heat from gravitational contraction, slowly cooling from its violent birth. Astronomers studying this system can observe planet formation processes in real time, watching how young worlds interact with their natal environments. The discovery challenges theories about planetary migration timescales, suggesting that hot Neptunes can form or migrate much faster than previously thought. What other infant worlds are taking their first steps in the cosmic nurseries of stellar formation regions? You're settling into extreme thermal contemplation now, pondering a world that pushes the absolute limits of planetary survival under stellar fire. TOI-2119b holds multiple records for extreme planetary conditions. Discovered by NASA's TESS in 2021, this ultra-hot Jupiter orbits its host star every 16 hours, the second shortest orbital period ever measured. Dayside temperatures reach 5,400 degrees Fahrenheit, making it the second hottest planet known. The Transiting Exoplanet Survey satellite detected this world's rapid transits, but ground-based follow-up revealed its record-breaking properties. TOI-2109b experiences some of the most intense stellar irradiation measured on any planet, receiving over 4,000 times more energy per square meter than Earth. At such extreme temperatures, the planet's atmosphere likely contains vaporized metals and exotic molecules that exist nowhere on Earth. The world's rapid orbit suggests it's spiraling inward due to tidal decay, possibly headed for destruction within the next 10 million years. Scientists believe TOI-2109b represents the extreme endpoint of planetary migration, a world that ventured too close to its star and now pays the ultimate price. What other worlds dance at the edge of destruction, testing the absolute limits of planetary endurance? You're wrapped in youthful cosmic light now, contemplating one of the youngest gas giants ever photographed, still glowing with the warmth of recent birth. TYC 8998760-1b made headlines in 2020 as one of the few exoplanets directly imaged by telescopes. Located 300 light-years away, this massive world orbits a sun-like star at a distance equivalent to 160 times Earth's orbit. The Very Large Telescope captured actual infrared light from this planet, revealing a world 14 times more massive than Jupiter. At only 17 million years old, the planet still radiates heat from its formation, glowing like a cosmic ember in the darkness. European astronomers used coronagraphic techniques to block the star's overwhelming brightness, allowing the planet's faint glow to emerge from stellar glare. The direct detection provides unprecedented insights into planetary atmospheres and formation processes. TYC 8998760-1. B likely formed through gravitational instability in its star's protoplanetary disk, collapsing directly from gas and dust rather than building up through core accretion. What other infant giants are glowing in the cosmic nurseries of distant stellar systems? You're drifting into gravitational complexity now, pondering a world that witnesses 3 suns rising and setting in its alien sky. Epic 2013-67065. D orbits within a rare triple star system, experiencing sunrises and sunsets involving 3 different stars. Discovered by NASA's K2 mission in 2015, this gas giant navigates the complex gravitational field created by its stellar trio. The planet orbits the primary star every 15.6 days, while 2 companion stars dance around each other in a wider orbit. This world experiences constantly changing illumination as its 3 parent stars move through complex orbital choreography. K2 photometry revealed the planet's transits across its primary star, but the gravitational influence of the stellar companions creates orbital variations that make long-term predictions challenging. Scientists studying this system discovered that planet formation can succeed even in chaotic multi-star environments where gravitational forces compete and interact. The planet likely formed in a stable region of the protoplanetary disk before the stellar system's architecture fully evolved. How do worlds survive and thrive in the gravitational chaos of multiple star systems? You're nestled in impossible survival now, contemplating a world that exists where no planet should, defying the cosmic wasteland known as the Neptune Desert. NGTS-4b earned the nickname the Forbidden Planet by existing in the Neptune Desert, a region around stars where mid-sized planets are extremely rare. Discovered in 2018, this sub-Neptune maintains a substantial atmosphere despite receiving intense stellar radiation that should strip it away. The Next Generation Transit Survey detected this anomalous world, orbiting a K-dwarf star every 1.34 days. NGTS-4b challenges our understanding of atmospheric retention, somehow preserving its gaseous envelope in conditions that destroy similar planets. Scientists believe the world might have migrated to its current position recently, before stellar winds could completely erode its atmosphere. Alternatively, the planet could be continuously replenishing its atmosphere through outgassing from its interior. The discovery suggests that the Neptune Desert might not be as empty as previously thought, with some worlds finding ways to survive the stellar bombardment. What other survivors lurk in the cosmic wastelands where planets aren't supposed to exist? You're breathing in orbital mystery now, contemplating a planet that orbits its star at such an enormous distance that it shouldn't exist according to current formation theories. HD 106906b defies conventional wisdom about planetary formation by orbiting 650 times farther from its host star than Earth orbits the Sun. Discovered in 2013 through direct imaging, this gas giant takes over 15,000 years to complete one orbit around its young stellar system. The planet formed in a debris disk that should have dissipated long before such a distant world could coalesce from dust and gas. Astronomers using the Magellan telescope captured infrared images of this distant world, revealing a planet 11 times more massive than Jupiter. The system also contains a prominent debris disk with a gap that might have been carved by the planet's gravitational influence. HD 106906b likely formed much closer to its star before being scattered outward by gravitational interactions with other planets or stellar encounters. This lonely world represents an extreme example of planetary migration, flung to the outer reaches of its stellar system. What other cosmic exiles drift in the cold darkness at the edges of distant planetary systems? You're settling into metallic serenity now, pondering a world where titanium vapor drifts through an atmosphere hotter than many stellar surfaces. WASP 189b experiences some of the most extreme conditions found on any planet, with dayside temperatures exceeding 5,800 degrees Fahrenheit. Discovered in 2018, this ultra-hot Jupiter orbits a bright A-type star every 2.7 days, tidally locked in perpetual stellar embrace. The Cheops Space Telescope revealed that this world has no detectable day-night temperature variation, suggesting extremely efficient heat transport through its atmosphere. Spectroscopic analysis detected titanium oxide and water vapor in gaseous form throughout the planet's atmosphere. The extreme heat prevents cloud formation, creating clear skies filled with vaporized metals that would be solid on Earth. Strong stellar winds from the hot host star constantly strip material from the planet's outer atmosphere, creating a tail of escaping gas. WASP 189b represents one of the most extreme examples of stellar planetary interaction, where a world exists at the absolute threshold of survival. What other impossible chemistry experiments are occurring in the furnace-like atmospheres of ultra-hot worlds? You're wrapped in binary wonder now, contemplating the largest planet ever found orbiting two stars simultaneously in a cosmic dance of gravitational precision. Kepler 11647b holds the record as the largest circumbinary planet discovered, orbiting two sun-like stars every 1,107 days. Found in 2016 through analysis of Kepler data, this gas giant is slightly larger than Jupiter and experiences double sunrises and sunsets like the fictional Tatooine. The planet orbits both stars at a distance similar to Earth's orbit around our Sun, placing it near the edge of the habitable zone. Complex gravitational interactions between the planet and binary stars create orbital variations that required years of careful analysis to confirm. The two host stars orbit each other every 11 days, creating a dynamic gravitational environment that somehow allows stable planetary orbits. Kepler 1647b likely formed farther from the binary pair before migrating inward to its current position. The discovery proves that large planets can form and survive in binary star systems, expanding possibilities for planetary architectures throughout the galaxy. How many other giant worlds are dancing around binary stars in the cosmic ballrooms of distant systems? You're drifting into metallic speed now, contemplating a world made largely of iron that completes one orbit faster than Earth completes one day. GJ 367b races around its red dwarf star in just 7.7 hours, making it one of the fastest orbiting planets known. Discovered by NASA's TESS in 2021, this sub-Earth world likely consists primarily of iron with little to no atmosphere. The planet receives over 500 times more stellar energy than Earth, creating surface temperatures around 2,700 degrees Fahrenheit. Ground-based radial velocity measurements confirmed the planet's mass and density, revealing a world denser than Earth despite being smaller. GJ 367b likely represents the exposed iron core of a former larger planet that lost its rocky mantle and atmosphere to stellar radiation over billions of years. The discovery required precise analysis of test data to detect the tiny 0.3% dimming when this small world transits its star. This ultra-short period planet provides insights into planetary core composition and the ultimate fate of rocky worlds around active red dwarf stars. What other planetary remnants race through the cosmos, stripped down to their metallic hearts by stellar fire? You're nestled in temporal patience now, contemplating a gas giant that breaks the mold by maintaining a distant, temperate orbit around its host star. TOI 2180b challenges assumptions about gas giant demographics by orbiting its star every 261 days at a comfortable distance. Discovered by citizen scientists in 2021, this Jupiter-sized world represents a rare class of warm Jupiters that maintain moderate temperatures and longer orbital periods. The transiting exoplanet survey satellite initially captured only a single transit of this world during its observation period, requiring follow-up ground-based observations to confirm its orbital characteristics. TOI 2180b receives similar amounts of stellar energy as Mars gets from our Sun, placing it in a temperate zone where water could theoretically exist in gaseous form. The planet's discovery came through collaboration between professional astronomers and citizen scientists analyzing test data. This world provides insights into gas giant formation and migration, suggesting that not all massive planets spiral inward to become hot Jupiters. TOI 2180b might represent what Jupiter would look like if observed from a distant star system. How many other patient giants are waiting in the outer regions of distant planetary systems? You're breathing in habitable possibility now, contemplating one of the most promising Earth-sized worlds discovered in the habitable zone of a nearby red dwarf star. LP 899c orbits within the habitable zone of a red dwarf star, just 105 light-years from Earth, making it one of the most accessible, potentially habitable worlds for future study. Discovered in 2022, this super-Earth receives stellar energy comparable to Venus, but orbits a much cooler star than our Sun. The Speculoos telescope network initially detected the planet's host star system, but follow-up observations revealed multiple worlds including this potentially habitable candidate. LP 890-9c completes one orbit every 8.8 days, likely tidally locked with permanent day and night sides. Computer models suggest the planet could maintain liquid water if it possesses a substantial atmosphere with greenhouse gases. The world's proximity to Earth makes it an ideal target for atmospheric characterization with the James Webb Space Telescope. Scientists believe LP 890-9c represents our best nearby opportunity to study atmospheric retention and habitability around red dwarf stars. What atmospheric secrets might be revealed when we finally peer into the skies of our closest potentially habitable neighbors? You're settling into tidal distortion now, contemplating a world stretched into an oval shape by its star's overwhelming gravitational embrace. WASP 103b has been deformed into a rugby ball shape by intense tidal forces from its nearby host star. Discovered in 2014, this hot Jupiter orbits so close to its star that it completes one revolution in just 22 hours. The Hubble Space Telescope measured the planet's precise shape by analyzing how starlight dims during transits, revealing an elongated world stretched by stellar gravity. WASP 103b's deformation represents the most extreme tidal distortion ever measured on an exoplanet, with the planet's shape noticeably different from a perfect sphere. The intense gravitational interaction also affects the host star, causing it to bulge slightly in response to the planet's presence. Scientists studying this system discovered that both the planet and star are slowly losing rotational energy through tidal friction, causing the planet to spiral gradually inward. WASP 103b provides a natural laboratory for studying tidal physics and the extreme limit of planetary structural integrity under gravitational stress. What other worlds are being sculpted into impossible shapes by the invisible hands of gravity? You're wrapped in size paradox now, contemplating a massive gas giant that shouldn't exist around one of the smallest stars in the galaxy. TOI 5205b challenges everything we thought we knew about planet formation around ultra-low mass stars. Discovered in 2022, this gas giant is nearly as large as Jupiter, but orbits a red dwarf star, only 1/5 the mass of our Sun. The Transiting Exoplanet Survey satellite detected this anomalous world, revealing a planet-to-star mass ratio 100 times larger than Jupiter's relationship with our Sun. According to standard formation models, such tiny stars shouldn't possess enough material in their protoplanetary disks to build massive gas giants. The discovery forced astronomers to reconsider how planets form around the galaxy's most common stars. TOI 5205b completes one orbit every 16.3 days, maintaining a surprisingly stable circular orbit despite its host star's small gravitational influence. This world proves that nature consistently surprises us, creating planetary architectures that defy our theoretical expectations. What other impossible pairings between planets and stars await discovery in the cosmic catalog of unlikely relationships? You're drifting into atmospheric clarity now, pondering a world with perfectly transparent skies that offer an unobstructed view into alien atmospheric chemistry. WASP 62b possesses one of the clearest atmospheres ever detected on an exoplanet, allowing astronomers to peer deep into its gaseous composition. Discovered in 2012, this hot Jupiter orbits its host star every 4.4 days while maintaining remarkably cloud-free skies. The Hubble Space Telescope detected strong water vapor signatures throughout the planet's atmosphere, unobscured by the clouds and hazes that typically shroud hot gas giants. WASP 62b's atmospheric transparency makes it an ideal laboratory for studying exoplanet weather and chemistry. Scientists discovered that the planet's extreme heat prevents cloud condensation, creating perpetually clear conditions despite temperatures exceeding 2,000 degrees Fahrenheit. The world's pristine atmosphere reveals the presence of sodium water vapor and possibly other molecular species in concentrations that would be hidden on cloudier worlds. This cosmic window offers unprecedented insights into the atmospheric dynamics of hot Jupiter planets. Why do the clearest atmospheric views often come from the most inhospitable worlds in the galaxy? You're nestled in cosmic isolation now, contemplating a massive world that orbits its star at such a vast distance that it barely feels its parent's gravitational embrace. HIPP 65426b exists in splendid isolation, orbiting its host star at 92 times the distance between Earth and our Sun. Discovered through direct imaging in 2017, this gas giant takes over 600 years to complete one orbit around its young A-type star. The Sphere instrument at the Very Large Telescope captured actual infrared light from this distant world, revealing a planet 6 to 12 times more massive than Jupiter. At such extreme orbital distances, HIP 654b receives minimal stellar heating, maintaining its warmth primarily through residual heat from formation. The planet likely formed through gravitational instability in the outer reaches of its star's protoplanetary disk, collapsing directly from gas and dust rather than building up through core accretion. This lonely giant challenges our understanding of planetary formation limits, existing at the boundary between planets and brown dwarfs in both mass and orbital separation. What other solitary worlds drift in the cold darkness at the edges of distant stellar systems? You're breathing in gravitational harmony now, contemplating a stellar system where 5 planets dance in perfect mathematical resonance like a cosmic musical composition. The K2-138 system contains 5 planets locked in a rare chain of orbital resonances, creating gravitational harmony unprecedented in exoplanet discoveries. Found by citizen scientists analyzing K2 data in 2018, these sub-Neptune worlds maintain orbital periods in nearly perfect 3:2 ratios with their neighbors. The innermost planet completes one orbit every 2.35 days, while each successive world takes approximately 1.5 times longer than its inner companion. This resonant architecture likely formed through synchronized migration inward from the outer system, with each planet maintaining gravitational locks with its neighbors. The discovery required careful analysis by volunteer astronomers, who noticed subtle periodic variations in stellar brightness. K2-138's resonant chain provides insights into planetary migration processes and the formation of compact multi-planet systems. The mathematical precision of these orbital relationships demonstrates how gravity can create order from the chaos of planetary formation. What cosmic symphonies are being composed by gravitational forces in the resonant architectures of distant worlds? You're settling into scorching similarity now, contemplating a world that mirrors Venus in size and temperature, but orbits an entirely different type of star. Speculoos 2b represents a near-perfect analog to Venus, but orbiting a red dwarf star instead of a Sun-like parent. Discovered in 2021, this Earth-sized world receives similar amounts of stellar energy as Venus while maintaining comparable surface temperatures around 900 degrees Fahrenheit. The Speculoos telescope network detected this world through precise transit photometry, revealing a planet with Venus-like characteristics in an alien stellar environment. Speculoos 2b completes one orbit every 8.5 days, tidally locked with permanent day and night hemispheres. The planet likely possesses a thick atmosphere with intense greenhouse heating, creating Venus-like conditions despite orbiting a much cooler star. This world provides opportunities to study how Venus analog planets form and evolve around red dwarf stars, the galaxy's most common stellar type. The discovery expands our understanding of planetary climate evolution in different stellar environments. How many other familiar planetary types exist around unfamiliar stars, creating alien versions of worlds we know? You're wrapped in orbital extremes now, pondering a gas giant that experiences the most dramatic seasonal variations imaginable as it follows a highly elliptical path. Toei 410b travels one of the most eccentric orbits known among transiting exoplanets, alternating between scorching heat and relative cold during its 134-day journey. Discovered by TESS in 2022, this gas giant swings from 0.25 to 0.87 astronomical units from its host star, creating temperature variations from 1,800 to 400 degrees Fahrenheit. The planet's highly elliptical orbit suggests a violent dynamical history, possibly involving gravitational interactions with other planets or stellar companions. During closest approach, TOI 4010b receives 45 times more stellar energy than at its most distant point, creating seasons of unimaginable intensity. Ground-based follow-up observations confirmed the planet's extreme orbital eccentricity and helped refine predictions of its atmospheric response to such dramatic energy variations. This world serves as a natural laboratory for studying how planetary atmospheres respond to rapidly changing stellar irradiation. What stories of cosmic violence are written in the eccentric orbits of worlds that swing between fire and ice? You're drifting into stellar rhythm now, contemplating a world that experiences constant brightness, variations as it orbits a star that pulses like a cosmic heartbeat. TIC 1729988b orbits a Delta Scuti variable star that pulsates with periods ranging from 20 minutes to several hours. Discovered in 2021, this hot Jupiter experiences constantly changing stellar illumination as its host star brightens and dims in complex pulsation patterns. The Transiting Exoplanet Survey satellite detected both the planetary transits and the stellar pulsations, creating one of the most complex light curves ever analyzed. TIC 1729988b completes one orbit every 1.1 days while bathed in the rhythmic glow of its variable parent star. The stellar pulsations create additional heating and cooling cycles that complicate the planet's atmospheric dynamics beyond simple day-night temperature variations. Scientists studying this system must separate planetary signals from stellar variability, requiring sophisticated analysis techniques. This world provides insights into how planets respond to non-steady stellar irradiation and the effects of stellar pulsations on atmospheric evolution. What other worlds dance to the complex rhythms of their variable stellar partners? You're nestled in orbital partnership now, contemplating a world that shares its stellar system with a close companion, creating a rare example of planetary coexistence. WASP 148c orbits its host star alongside WASP 148b in one of the few confirmed multi-planet systems where both worlds transit their star. Discovered in 2020, this outer gas giant takes 34.5 days to orbit, while its inner companion completes the journey in just 8.8 days. The two planets maintain a stable orbital configuration despite their gravitational interactions, which create measurable timing variations in their transits. WASP 148c likely formed farther from its star before migrating inward to its current position, while gravitational interactions with its companion helped stabilize both orbits. The system provides rare insights into how multiple gas giants can coexist in close proximity around the same star. Transit timing variations reveal the precise masses and orbital evolution of both worlds, offering a detailed view of planetary system architecture. This pair demonstrates that giant planets can maintain stable partnerships even in compact orbital configurations. How many other planetary partnerships exist in the crowded inner regions of distant stellar systems? You're breathing in atmospheric expansion now, contemplating a world puffed up by stellar heating to densities lower than styrofoam. L168-9b maintains one of the lowest densities ever measured for a sub-Neptune planet, inflated by stellar heating to a density just 60% that of water. Discovered by TESS in 2021, this world orbits a nearby red dwarf star every 1.4 days, while somehow retaining a substantial atmospheric envelope. The planet's extreme inflation suggests ongoing atmospheric heating from its host star's X-ray and ultraviolet radiation. L168-9b likely possesses a small rocky core surrounded by an enormously expanded hydrogen-helium atmosphere that fills a volume much larger than the planet's mass would normally allow. The world exists at the edge of atmospheric retention, slowly losing material to space while maintaining its bloated structure through continuous stellar heating. Ground-based spectroscopy revealed possible atmospheric escape signatures, confirming that this world is gradually evaporating. This inflated planet provides insights into atmospheric loss mechanisms and the transition between rocky and gaseous worlds. What other cosmic balloons are being inflated by stellar radiation in the space between rocky planets and gas giants? You're settling into satellite serenity now, contemplating humanity's second confirmed detection of a moon orbiting a distant planet, expanding our understanding of satellite systems. Kepler 1708b represents only the second confirmed exomoon discovery, orbiting a gas giant located 5,500 light-years away in the constellation Cygnus. Detected through analysis of Kepler data in 2022, this moon creates subtle variations in its host planet's transit timing and depth. The exomoon likely measures 2.6 times Earth's radius, making it larger than any satellite in our solar system while orbiting a Jupiter-sized planet. The discovery required years of careful analysis to separate the moon's gravitational signature from stellar noise and instrumental effects. Kepler 1708b orbits its parent planet at a distance similar to our moon's relationship with Earth, but its massive size suggests formation through planetary collision or gravitational capture. The confirmation of a second exomoon opens new possibilities for satellite system architectures around distant gas giants. This discovery demonstrates that large moons may be common throughout the galaxy, potentially harboring their own unique environments and evolution stories. What other satellite worlds are waiting to be discovered in the gravitational embrace of distant gas giants? You're wrapped in interstellar cold now, contemplating one of the first rocky worlds discovered in the frozen outer regions where ice dominates over liquid water. Ogle 2005 BLG 390LB became a landmark discovery as one of the first confirmed super-Earths found through gravitational microlensing. Detected in 2005, this frozen world orbits a red dwarf star at a distance where surface temperatures plunge to 350 degrees Fahrenheit. The planet contains about 5.5 times Earth's mass while maintaining surface conditions similar to Antarctica's most extreme regions. Polish astronomers monitoring gravitational lensing events noticed the characteristic light curve signature that revealed this distant world. The discovery proved that rocky planets could form and survive in the cold outer regions of stellar systems, far beyond traditional habitable zones. Ogle 2005 BLG 390LB likely possesses a thin atmosphere of nitrogen or methane, with any water existing only as solid ice. This world opened our eyes to the possibility of frozen super-Earths throughout the galaxy. What other ice worlds drift in the cold darkness beyond the reach of their parent star's warmth? You're drifting into temperate possibility now, pondering a massive rocky world that might maintain liquid water in the comfortable embrace of its star's habitable zone. HD 40307G orbits within the habitable zone of a nearby orange dwarf star, receiving stellar energy similar to Earth despite being 7 times more massive. Discovered in 2012 through radial velocity measurements, this super-Earth completes one orbit every 197 days while maintaining potentially temperate surface conditions. European astronomers spent years analyzing tiny stellar wobbles to detect this world's gravitational influence on its host star. The planet's size suggests it could retain a substantial atmosphere capable of supporting liquid water oceans. HD 40307G became one of the first super-Earths considered potentially habitable, sparking discussions about how gravity and atmospheric pressure might differ on massive rocky worlds. Computer models suggest the planet could maintain stable climates for billions of years. This world represents an early example of discovering potentially habitable planets larger than Earth, expanding our definition of worlds where life might exist. Could massive rocky worlds like this harbor life forms adapted to higher gravity and thicker atmospheres? You're nestled in orbital cooperation now, contemplating a warm, gaseous world that shares its stellar system with 4 other planets in gravitational balance. Kepler 296e orbits within a 5-planet system where all worlds maintain stable, nearly circular orbits around their host star. Discovered in 2014, this warm Neptune receives moderate stellar heating while existing alongside 4 planetary companions. The Kepler mission detected all 5 planets through simultaneous transit observations, revealing a compact system with complex gravitational interactions. Kepler 296e likely maintains a thick hydrogen-helium atmosphere with possible water clouds in its upper regions. The planet's moderate temperature and substantial atmosphere make it an intriguing target for studying atmospheric chemistry on gaseous worlds. Scientists analyzing this system discovered that multiple planets can coexist in close proximity while maintaining stable orbits over billions of years. The gravitational dance between all 5 worlds creates subtle timing variations that help astronomers measure planetary masses and orbital evolution. This world demonstrates how planetary systems can achieve long-term stability through careful orbital choreography. How many other multi-planet systems maintain such delicate gravitational balance across cosmic time? You're breathing in gravitational locks now, contemplating a massive rocky world caught in perfect orbital synchronization with its giant planetary neighbors. Gliese 876d orbits in gravitational resonance with 2 gas giant companions, creating a stable 3-planet system locked in mathematical harmony. Discovered in 2005, this super-Earth completes exactly 4 orbits for every 1 orbit of its outer giant companion. The planet likely maintains surface temperatures around 650 degrees Fahrenheit due to its proximity to the host red dwarf star. Astronomers detecting this world through radial velocity measurements discovered that gravitational resonances can preserve planetary system stability over billions of years. Gliese 876d became one of the first confirmed rocky planets around a red dwarf star, proving that terrestrial worlds can form around the galaxy's most common stellar type. The planet's resonant relationship with its gas giant neighbors demonstrates how gravitational interactions can lock planets into stable long-term configurations. This world provided early evidence that super-Earths might be common around low-mass stars. What role do gravitational resonances play in preserving planetary systems throughout cosmic evolution? You're settling into observational breakthrough now, contemplating one of the first planets discovered by a dedicated space-based transit survey mission. CoRoT-1b became one of the first exoplanets discovered by the French CoRoT Space Telescope, marking the beginning of systematic space-based planet hunting. Found in 2007, this hot Jupiter orbits its host star every 1.5 days, while enduring surface temperatures exceeding 3,600 degrees Fahrenheit. The CoRoT mission demonstrated that space telescopes could detect planetary transits with unprecedented precision, opening new frontiers in exoplanet discovery. CoRoT-1b helped validate the transit method as a powerful tool for finding distant worlds, paving the way for future missions like Kepler and TESS. The planet's discovery proved that hot Jupiters were more common than previously thought, reshaping theories about gas giant migration. Scientists studying CoRoT-1b's atmosphere detected possible water vapor and carbon monoxide signatures. This world represents a milestone in exoplanet science, demonstrating humanity's ability to systematically survey the galaxy for planetary companions around distant stars. How did this pioneering discovery help launch the golden age of exoplanet exploration we experience today? You're wrapped in precise measurements now, contemplating a world whose orbital variations revealed the power of transit timing analysis in planetary discovery. XO-1b became one of the first planets where astronomers successfully used transit timing variations to study planetary system dynamics. Discovered in 2006, this hot Jupiter provided early demonstrations of how gravitational interactions between planets create measurable changes in orbital periods. The XO project detected this world through ground-based photometric monitoring, but follow-up timing studies revealed subtle orbital variations caused by unseen planetary companions. XO-1b's transit timing changes helped astronomers develop techniques for detecting non-transiting planets in multi-planet systems. The planet maintains surface temperatures around 2000 degrees Fahrenheit while completing one orbit every 3.9 days. Studies of XO-1b's orbital evolution provided insights into how tidal forces between planets and stars affect long-term system stability. This world helped establish transit timing as a powerful complementary technique to traditional discovery methods, expanding astronomers' ability to characterize complex planetary systems. What other hidden planets might be revealed through the subtle gravitational tugs recorded in transit timing data? You're drifting into atmospheric inflation now, pondering one of the largest known exoplanets, inflated to impossibly low densities by stellar heating. TURS-4b holds records as one of the largest exoplanets ever discovered, with a radius 1.8 times larger than Jupiter despite containing similar mass. Found in 2007, this ultra-hot Jupiter maintains a density lower than Cork while orbiting its host star every 3.6 days. The Transatlantic Exoplanet Survey detected this bloated world through careful photometric monitoring of stellar brightness variations. TURS-4b's extreme inflation demonstrates how intense stellar heating can puff up planetary atmospheres far beyond normal limits. The planet likely exists at the edge of atmospheric retention, slowly losing material to space while maintaining its bloated structure through continuous stellar energy input. Scientists studying TURS-4b discovered that gas giant atmospheres can expand to fill volumes much larger than their mass would normally allow. This cosmic balloon provided early evidence that hot Jupiters could achieve densities approaching those of Earth's atmosphere at sea level. What physical processes allow planets to maintain such impossibly low densities in the face of their own gravity? You're nestled in orbital misalignment now, contemplating a gas giant whose tilted path around its star suggests a violent dynamical history. P32b orbits its host star at an angle tilted 85 degrees from the stellar equator, indicating a chaotic formation or migration history. Discovered in 2011, this massive hot Jupiter contains twice Jupiter's mass while maintaining an orbital period of just 2.2 days. The Hungarian Automated Telescope Network detected this world through transit photometry, but spectroscopic follow-up revealed its dramatically misaligned orbit. P32b's tilted orientation suggests it experienced violent gravitational interactions during its youth, possibly with other planets or stellar companions. The planet's extreme orbital misalignment challenges standard theories of gas giant migration through smooth disk interactions. Scientists believe P32b might have been scattered into its current orbit through planet-planet interactions or encounters with binary star companions. This world demonstrates that planetary system architecture can result from chaotic and violent processes rather than orderly formation sequences. What cosmic violence shaped the tilted orbits of misaligned planets throughout the galaxy? You're breathing in backwards motion now, contemplating a bloated world that orbits in the opposite direction to its star's rotation, defying conventional formation wisdom. WASP-17b travels backwards relative to its star's rotation while maintaining one of the largest planetary radii ever measured. Discovered in 2009, this retrograde giant completes one orbit every 3.7 days while somehow achieving a radius twice that of Jupiter, despite containing half Jupiter's mass. The Super-WASP survey detected this anomalous world through transit photometry, but its backwards orbit posed immediate puzzles about planetary formation. WASP-17b's retrograde motion suggests it experienced violent gravitational scattering events that flipped its orbital direction during system evolution. The planet's extreme inflation likely results from tidal heating caused by its unusual orbital configuration and proximity to its host star. Scientists studying WASP-17b discovered that planetary migration can proceed through chaotic pathways that completely reverse orbital directions. This backwards world challenges our understanding of how planetary systems achieve their final architectural configurations. How many other worlds orbit in cosmic rebellion against the rotational direction of their parent stars? You're settling into the dawn of a new era now, contemplating how the James Webb Space Telescope is revolutionizing our ability to study the atmospheres of distant worlds. The James Webb Space Telescope represents humanity's most powerful tool for studying exoplanet atmospheres, capable of detecting individual molecules in the skies of distant worlds. Since beginning operations in 2022, JWST has analyzed dozens of exoplanet atmospheres with unprecedented precision, revealing water vapor, carbon dioxide, clouds, and hazes in extraordinary detail. The telescope's infrared capabilities allow it to peer through cosmic dust and analyze starlight filtered through planetary atmospheres millions of miles away. Scientists using JWST have detected atmospheric compositions, temperature profiles, and weather patterns on worlds ranging from hot Jupiters to potentially habitable super-Earths. The telescope's sensitivity opens possibilities for detecting biosignatures, signs of life, in the atmospheres of Earth-like planets orbiting nearby stars. JWST observations are transforming exoplanets from distant points of light into complex, individual worlds with unique atmospheric personalities. This revolutionary capability marks the beginning of detailed comparative planetology across interstellar distances. What atmospheric secrets will we discover as we peer into the skies of potentially habitable worlds in our cosmic neighborhood?